Alright, so in the last two tutorials, we have built linear models which deal with predictor variables which are categorical. Different groups is kind of how the predictor variable manifests in those cases. So what we're going to do now is learn how to build linear models when our predictor variable is not categorical, when it's perhaps continuous or kind of discrete at an ordinal level where there's ranks to different groups. And so in order to do this, let's load in a different data set. For a bit of variety, we're not going to use the ArcData package this time. We're going to use the Broughton 1994 data set on animal bones from the Sacramento Valley. This file is available to you. I've already got it saved in my working directory, which I've set up here. So you'll need to set your working directory to get this if you haven't already. And so let's load this data in. I'll call it sac data for Sacramento Valley. Use the read CSV function to call up Broughton 1994 JAS Sacramento Valley.csv. So if I run that, now I've got this sac data object in my environment. Let's inspect this object, see what we're dealing with here. Make this a little bit larger, see if I can fit it. Yes. So with the head function, what that does is show you the column names and then also the first 6 rows, so you can kind of get a sense for what the data look like and what different columns we're dealing with here. You can also simply, of course, just use call names on the data frame, and that'll give you just the column names. We can also do nrow, which will tell you how many rows exist in the data. In this case, we've got all these different columns, site, date, a couple different columns for different animal bone counts, and then 2 columns for indices calculated from those. And we know we have 9 rows based on all of this. What we're going to do here is build a model based on this FM index column. The FM index in this case is something that I calculated based on Broughton 1994, the data that he provided in that paper. If we pull it up here and run that, we can see what these values are. There's 9 different values. And what these represent are actually, it's an index calculated based on the fish remains and mammal remains. Basically, I ran a mathematical operation that compared the relative abundance of fish to mammals, hence FM index. And basically, when this index value is positive, there are more fish bones than mammal bones. When the index is negative, there are more mammal bones than fish bones. And so if we look at the values we've got down here for the FM index, right, these negative values, those are going to be cases when there are more mammals relative to fish, and the positive when there are more fish relative to mammals. These data, they're in the form of decimals, so we know that they're kind of continuous. They're ranging to positive and negative values, so we know that they're kind of coming from a normal distribution, potentially. And that means that we can use the LM function, linear model, to do this. But of course, before we begin modeling anything, let's plot our data. Do FM index as a function of date. There's a date column in here as well, and data equals sac data. We'll plot that. Expand the window a little bit, and you can see here that we've got date running from the present on the left, 0, back in time, more than 3,500 years BP. And this FM index value right here, the middle of the plot, is a value of 0, and so it looks like closer to the present it's more positive, and then further back in time it's more negative. A lot of archaeologists don't like plots constructed this way, where the present is on the left. A lot of them tend to prefer that time move from left to right, from the past to the present, and therefore present or year zero is at the right of the plot. I'm not really particular either way. I think there's arguments to be made for doing it this way as well, but for the sake of kind of jiving with what many archaeologists prefer, we can flip the axis simply by using the xlim argument in our plot function, and saying xlim equals concatenate 4,000, 1 or 0, and so this will then make the axis run from 4,000 BP on the left to 0 on the right, and that'll just allow us to kind of perhaps visualize what's going on here in a way that's more familiar to us and makes more sense to our brains. And so based on this, it looks like earlier in this archaeological record, before about 2,000 years ago, maybe 2,000 to 4,000 years ago, this index value is really negative, which suggests that there were more mammals than fish in these archaeological assemblages. However, after about 1,000 years ago, it looks like there's a lot more fish than mammals in this index, and a bit of a transition period in between. So there's a bit of a pattern here from kind of negative values of the FM index to positive values as we move towards the present. But of course, just looking at this plot, even if we can tell that there's something going on, we don't actually know or have any numbers associated with this about whether this is a strong trend, or if it's even statistically significant, which might be something you care about if you're into frequentist statistics. And so let's actually build a model to investigate this. To build this model, let's call it SACMod. Let's use the LM function, because we've discussed that these data are able to be negative or positive. They are in the form of decimals, so they seem to be continuous. So an LM function is a reasonable thing to use in this case. So let's plot the FM index, or rather model the FM index as a function of date using all of SAC data, and we run that model, and there we have it. But of course, before we actually begin to interpret the model, we've got to make sure that we're not violating any assumptions. So we plot the model diagnostics. If I've just run that code and go down to the Arc console and hit enter, it brings up the first plot, the residuals. The red line, of course, it's a little squiggly, not perfectly along that dotted gray line, which is what we want. But a lot of this is driven by the fact that there's only 9 points in this data set, so it's not a huge data set, and that means that these residuals are going to impact that shape a little bit more. But it's still reasonably kind of a horizontal pattern. It doesn't look like there's any weird stuff going on in these residuals. There aren't many of them to see if there's anything going on, but they look good to me. In the next plot, the QQ plot, it looks like the residuals are also normally distributed. Again, like that number 4 point at the low value of the theoretical quantile is starting to deviate from normality, but everything's pretty much along that line. I don't think this is going to be any problem for us. The third plot of the standardized residuals, that red line, again, shouldn't be trending upwards or downwards, and it's not really. It's kind of, you get the impression that it's trending downwards because of this last point here, kind of drags that red line down, but pretty much all of these are straight across. This doesn't look like there's any egregious heteroscedasticity to me. And then finally, our plot of the kind of the leverage of these points with Cook's distance. Now you can clearly see these kind of confidence intervals of Cook's distance. And we see that we actually do have a data point, the first data point, which is outside of the first of these. And this suggests that that data point is having perhaps a bit of an outsized influence on our model fit. Most points are good. It's just that one that's out there. Now, some people would begin to think about removing this first data point if it's some outlier that's causing problems in the model. But I don't generally use this plot to decide whether or not to remove data from my data set. I think that you shouldn't be removing data at all from your data set under the vast majority of conditions. And so this plot is really just telling me that I should probably inspect the model fit and make sure that there's not some weird thing going on where I've just got one point way out there and everything else is clustered. And if I got rid of that point, would there be no trend at all, right? But of course, we plotted the actual data. And if I go back to that plot right here, we can see that it's not like we've got no trend and then one point way off in space that would create a trend. There is a trend here that exists, and even if one of these points is having a bit of undue influence on the model, I don't think that's a problem. And so again, qualitative interpretation, it's a bit subjective interpreting these diagnostic plots, but use your own judgment and think about what they're telling you, and look at your actual data plotted here. And imagine that line fitted there, which we'll plot later, and just think if that makes sense. I'll continue with that discussion in a bit, but this is how you would kind of go about initially assessing the diagnostics for this. And now you've seen what diagnostic plots look like for models that don't have just categorical or categories in the predictor variable, but have continuous predictor variables. Whereas before, in our t-test and ANOVA type models, we had these vertical rows of residuals because they were in groups. Now they're all spread out across here because we're no longer dealing with grouped or categorical predictor variables, but continuous ones in this case.